Good morning, good morning, good morning. Good morning. Believe I'm recording now? Yes. A most wonderful good morning. Good morning, good morning, good morning. Please come in. Morning, good morning. Good morning.
Hi, I'm not one of your students.
Good.
I'm looking for a workshop, and it said
Which is?
it said GLT2 by Jose.
By Jose.
Yes, Ortega.
Do you want to come in?
I'm a PhD student. I don't know what class you're teaching.
Statistics.
Ah. Revisions of data analysis, data types, and key concepts.
Sounds about right.
Okay.
So you're in the right place.
I guess I am.
PhD. Who are you doing your PhD with?
Becky.
Becky Hall.
Yes, but I have no idea how to do stats.
Really?
I'm not very good at it.
No. Wrong. You're not very good at it yet.
Oh, that's too optimistic.
No. You will be.
So when it says lectures in GLT2, that'll be for this. Thank you.
All yours. $23. Aha. Is the light all right, or is it too dark? Do you want it? Do you want it more light? Yeah. More light. Slightly more. Let's see if I can do slightly more. Ah, good morning. Is that better? Good. What is this? That's not mine. Almost wonderful. Good morning.
Good morning.
I'm very well, thank you. And your good self?
Fine, just can't remember what lecture date I'm supposed to be in.
Sorry?
Can't remember what lecture date I'm supposed to be
You're
in.
probably in here.
Okay, thanks.
Not with me this time.
Anyway, I'm with you.
And you, take care. Be good. Good morning. Good morning. Good morning. Okay, let's make a start, right? A most wonderful good morning, ladies and jelly beans. And a very warm welcome to this, actually, I don't know exactly what it's supposed to be, sort of statistics, data analysis thing for, initially it was meant to be for the MSCT students in biosciences, but then we had this idea to open it to a wider audience because we felt that maybe statistics and data analysis might be of some interest to people because it's something that hits us basically every day. My name is Peter Klapper. Let me write that down. And together with my colleague, Dr. Chris Mulligan, we will take you through this module, the research skill module for the MSCT students. But everybody else is also very welcome. Can I just quickly do a show of hand? Who is actually registered for the MSCT research skill module? Hands up, please. 1, 2, 3. It's not a lot, right? Okay. Now we do the odds ratio for that. Who is not registered for the MSCT? Hands up. There must be quite a few other people. Okay, good. Excellent. Thank you very much. Nevertheless, you are very welcome. Those of you who are registered, can I quickly check with you how many of you guys who are MSCT students have done their undergraduate degree here at Kent? You have? You have 2, 3. Good. Excellent. So the rest, obviously, not. Right. Now, for the MSCT students, you need to register your attendance. I don't know whether you have done that or you have been shown. Basically, we have different codes for different modules that you are doing for different programs. I have absolutely no idea what BIOS 8630 is. You probably know that. Good morning. You probably know that. And what you need to do is you need to put in these 6-digit code into the attendance field on Moodle. You can scan this QR code. Have you already registered your attendance with that? Those.
The easiest way I found is going into the Kent student app and then going into key links, and they have Presto as an option.
Yeah, that will go into Presto.
Yeah.
Okay, so everybody's done the registration. Brilliant, good.
I haven't done the attendance
So
I'm currently on the site on Presto, but I'm not sure what exactly I need to put here.
you would need to put the. I don't know.
Let me show you. Wait.
Okay.
Yes, I do.
Oh, you go to your timetable. Yeah, that's a good. Thank you. That's a good shout. Okay. If you do have problems with the registration, there is something called the Nexus in the library or something like that. They might be able to help you. But as you just said, if you go to your timetable, you should be able then to register and put these one of these 3 codes in it. Every year, the system gets more complex and complicated and costs more money. I think that is probably done deliberately. Anyway, as I said, my name is Peter Klapper. Just a little bit of housekeeping. In the first place, people usually refer to me either as Peter or Dr. Klapper, if they want it a little bit more formal, or they also call me Dr. Peter if they want to have something in between. Whatever is absolutely fine. I don't take any offense. What I don't really appreciate is if you get an email saying, "Oi, Klapper." That's a little bit, if you do that to one of my colleagues, you will get probably a long rant about being disrespectful and things like that. From me, you simply don't get an answer. End of story. So, right. In terms of, I fully understand we have a wide spectrum of people here with skills. And if you feel that it is far too easy, what I'm doing, please do feel free to just simply wander out, do something better with your time. You don't have to sit here. If you've got any questions, comments, remarks, please shout out. From my point, it is very difficult sometimes to see a raised hand. And I'm almost blind anyway, so I can't see that. So that should just be brave. Phones, I would very much appreciate if they are on silent, unless you are really waiting for this crucial phone call saying that your kidney transplant is ready. Right. So what we are going to do I think we've got 4 of these 2-hour workshops. The plan is to have a little bit of a break in between because 2 hours of statistics, that is, is banned under the Geneva Convention. And most of the stuff that you will encounter is probably a revision and repetition. It's important because the reason why I'm harping on about that is when I supervise dissertations, for example, or research projects, be it at whatever level, undergraduate, postgraduate level, sometimes you just think, no, 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 no. This is not how you do it. And I will come back to that a little bit later. When things really go wrong, then it's usually because the basics are not there. Okay? But if it is too simple and too easy, please let me know. And I can, hopefully entertain you with more exciting stuff. Okay. I have set up a website for you guys, which is called Advanced Research Skills. And that hopefully covers a lot of the aspects that we are dealing with, but also are important when you do actually research. That you, for example, understand okay, I take that as an agreement, that you understand, for example, how experiments are designed. And there are different ways of designing experiments. How to write a good abstract. That is an art, and those are on the MSCT will actually be assessed on that. Let me just quickly switch over while we are talking about assessment. So here is the Moodle page, and you find all the information about what we are doing with you. On this Moodle page, you have basically 2 assessments, and they are equally weighted. One is called peer review assignment, which is total nonsense because there's very little peer review. It is basically a statistics assignment. But when you do a peer review, if you read, for example, a research paper, you need to ask the right questions, and you need to understand what have they done in terms of data analysis. So this peer review assignment, that is with me, where I will give you a few statistics questions, and then you do the calculations, and it's all easy peasy and nothing to worry about, right? 50%. If you get less than 80%, I will be mortally offended. The other one is research proposal presentation. Breathe easy. There is no presentation. You don't have to stand up in front here and do a presentation or something like that. But it will be something that my colleague, Dr. Mulligan, is going to do with you, where you, for example, look at a data set where you come up with meaningful research questions. And that is one of the big things that hopefully you will learn in this module, how to formulate meaningful research questions. Research questions that you can actually analyze. It's great if you say, right, my research question is, how does cancer work? Fantastic, yeah? It's a big question. But at the end of the day, if you want to do research, is you want to test, for example, whether drug A is more effective than a placebo when it comes to lung cancer. And that is what I mean by meaningful and quantifiable research questions. How do you formulate these things? And that is hopefully something that you're going to learn in this module. It is recorded. I hope so. Yeah, that brings me to the next point. I will try to record all sessions that you do with me. So if you say something inflammatory or something you feel, well, leave it up to me to talk nonsense. Because then you will be on the recording as well. Okay. What else? I think that's more or less what I wanted to talk about. You've got a sort of a tentative schedule, what we are going to do together. And right. Any questions about things so far? Please make use of this website. I took a long time to put everything together. Reading list, books, etc. I recently put out what I think is probably a decent book about data analysis, and that is sort of that covers pretty much all the aspects that we are doing in this module, plus more. It shows you how to do things with Excel. How many people would say they are really savvy with Excel? Hands up. They can do statistics with Excel. Not that many. Okay, interesting. Excel is pretty good. It's really good if you know what you're doing. And I thought for a long time, well, why should I come up with anything else other than Excel? There are things that Excel is not very good at, and where you run into problems that Excel can't help you with. And we will hopefully discover a few of these things. The alternative to Excel is R. How many people have experience with R? Hands up. 1, 2, 3, 4, 5, 6. So you've done programming in R? Yes, a little bit. RStudio, brilliant. Because that, what is your view on R? Good, bad, ugly? Complicated. I love it. I love you. Because I love it. So your friend is my friend. R, brilliant. I will give you at the end of this session today a very brief overview of R and how to install it on your computer. It is definitely worth exploring because so far I have not come across even a very complex statistic problem that you can't address in R. And it is just brilliant. The programming, some people say it's very complicated. I'm of the opinion that if you sort of start from scratch, it's not that complicated. It always does the same thing, and it has fantastic help functions, but I will discuss that later. Okay, do you have any questions? God, I'm good. Okay, well, let's get started with probably something incredibly basic. But this is usually where things go wrong when people do research. Let's start with descriptive statistics. And in the first place, what we need to do is be very clear about the different data types and data formats that we might encounter. Because these data types then will inform what kind of statistical analysis you can do with them. And if you get that in the first place, if you get that wrong, basically your analysis is BS. Okay, so we have different ways how we can categorize data. The probably easiest way, or the sort of most intuitive way, is to categorize the data into what do they look like. So, for example, we can have what is called nominal data. Nominal data just include data that are just simply descriptive, that are, if you like, a label. So, for example, male, female, non-binary would be nominal data. So there is no value attached to the data. There's no way intrinsic order attached. Male is not better than female. things like that. That doesn't make sense. Cat, dog, goldfish, snake. It's just sort of categories. So these are categorical data, if you like. These data are usually not associated with numbers, but we can attribute numbers to them by just simply saying, okay, how many of a certain label do we have? So we can count the frequencies. So, for example, in my household, we have 3 cats and 2 dogs, and I can categorize that. By the way, cats are evil. How many people like cats? Hands up. Okay. How many people like dogs? Hands up. Oh, thank God for that. The cats are the spawn of Satan. Okay. Sorry?
I said, should we write that down?
If you want. I don't want to be quoted on that, but you know, cats. A cat sits on the chair, dog walks past, the cat goes like, the dog like, what happened? Why? Why me? And the cat goes like, next time the dog comes past, I whack him again. Evil. So I can associate frequencies to that. Another way of categorical data is if we associate a sort of a value attribute to them, and then we've got ordinal data. Ordinal data are labels again, but there is a sort of a hierarchy in them. For example, gold, silver, and bronze medal. A gold medal surely is more worth than a silver, is more worth than a bronze medal. So you see there is an order in it. However, this order is not terribly well defined. How much more is a gold medal worth than a silver medal? It's very difficult to pin down. But again, we can do frequencies with these as well. Not a problem. And say a country won 35 gold medals and 16 silver medals. And then you can do these medal tables. And then people struggle a little bit. Which country is best? How much do you attribute to a gold medal compared to a silver medal? It's a little bit difficult, but there is an order in it, and you can, again, attribute frequencies. The third one is a little bit more specific. This is usually called numeric data or scale data. And here, you're not necessarily working with labels like in the categorical data. You are then working with, you know, for example, measurements, where you actually have numbers. And you can have what is called ratio data or proportions or ratios. The difference is a little bit murky. Usually, proportion would be something along the line of there is no physical meaningful zero. That is what people usually say when they talk about proportions. So when you talk about, for example, the temperature in a Celsius scale, there is a zero, but that is a very sort of why is the freezing point of water 0? What does that mean? Why do you choose that? Whereas if you have the Kelvin temperature scale, you can have 0 degrees Kelvin, which means there is no movement. That is no movement, nothing, end of. So that would be a ratio scale. But you see, it's a little bit diffuse. Very often, however, these numerical data are not necessarily grouped into these proportion and ratio data. More useful would be probably more useful probably would be if we split these data into discrete data. Discrete. I can't properly write. And continuous data. That is probably more useful, especially when we analyze data in statistics, because there are huge differences between these data sets. So what are discrete data? Discrete data is one data point taken, and the next possible data point that you can take is separated from the first one, and there is nothing in between. There cannot be anything in between. So you have one and another one here. Nothing in between. Let me give you an example for a discrete data point. The number of people in this room could be, I haven't counted, 35, or it could be 36. But it cannot be anything in between unless you are pregnant. But we don't count that, right? So it can only be 35 or 36. It cannot be 35.28. And you see the relationship between discrete data and the categorical data, where we count frequencies. So if I count the number of penguins or number of stars in a certain sector, it will be a whole number, and it is a discrete number. On the other hand, continuous data are basically a continuum. So you've got your two measurements, but anything in between is possible. You might not necessarily be able to measure it, but it would be possible if your measuring device had a higher precision or something like that, or a higher resolution. So if I, for example, measure the height of a student, 178 centimeters, if I use a more precise tool, it would be 178.2 centimeters. Would be 178.2567903 centimeters, and so on and so forth. So this is basically the thing with the continuous data. It could be loads on loads of data. Actually, an infinite number of data points could be in between the next potential measurement. Makes sense, right? It's very easy. How do we find out whether data are discrete or continuous? Obviously, it's one of the problems. If it is so important, very often a good giveaway is if the data have a decimal point in it. So if it is 178.2 centimeters, that indicates 0.2 indicates, oh yeah, well, look, it could be 0.2, 0.25, 0.24 or something like that. So that means continuous. Need a little bit of care because, for example, I hazard a guess, 24 out of 30 people here know about statistics. Okay? That gives us, what does that give us? 24 divided by 30 is 0.8, right? Did I get this right? Hope so. Continuous or discrete? Continuous? Is it continuous or discrete? Okay. We've got a decimal point, a 0.8, so that indicates it might be continuous. What would be the next value that we could potentially measure? It would be 25 over 30, or it would be 24 over 30, or 23 over 30, right? So you've got two measurements, and there can't be anything in between. So we would consider such a ratio as a discrete data, although it has a decimal in it. Make sense? Fantastic. Okay, so we now know, okay, this is one way. We are only dealing here with a single set of data. But of course, we could also have more complex data sets where we have what is known as bivariate data. Where you don't have just a single set of data, where the data are, for example, you've got two variables, namely, let's say an x variable and a y variable. And this x might be somehow related to the y. In this case, we would usually denote x as our independent variable. That means that is the variable over which I have control. So for example, I want to look at a relationship between height and weight, mass of a student. And I would go along, have a sort of my tape measure, thank you, that was the word I was looking for. My tape measure, measure students and say, okay, this is the height of the student, and then I want to develop a relationship. How is that related to the mass? So your x value is usually the independent, that is what I have control over. It is also frequently called the predictor variable. And the y variable, that is, if you like, what I measure. That is what is dependent on the x value. So that would be the dependent. Sometimes called the response variable. And also very often called the outcome, or just simply the result variable. And we probably will discover that this is a sort of, again, is an oversimplification. Of course, the x independent, the predictor variable, can be any of the categories that we've defined. It could be, for example, a numerical or nominal. It can be a nominal variable. It could be ordinal. It could be discrete. It could be continuous. It could be that the y variable, our response variable, is continuous. Could be that it is discrete. It could be that it is nominal or ordinal. So there are combinations possible, and each combination actually requires a different way how we actually address these things. And you need to be careful, because if you choose the wrong sort of attempt to analyze the data, then basically everything gets totally messed up. So it's really important that we are very clear about these data sets. So far, very easy, right? Nothing terribly exciting. Let's have a quick look at how we can describe now data. And let's focus predominantly on continuous data. Because it's easier and it's more intuitive to make sense. Let's describe data. Let's say I have measured all you guys here, the height, so I get a data set. So data set, continuous data set, let's put it this way. Or let's do something better. I give you a data set, and we use that sort of as a toy data set for us. Let's say the data set is not the height. The data set that I give you is 1, 2, 3, 4, 5. That's our data set. The sample size, usually abbreviated with n, that's the sample size, of course, is 5. Okay, continuous or discrete? It's just the numbers. I just given you numbers, 1, 2, 3, 4, 5. Continuous or discrete? Sorry? Discrete? You're absolutely right. So, discrete, yeah? You're absolutely right. Actually, no, you're not right. We have no idea what these data actually represent. You're totally right. It could be discrete if we, for example, count, let's say, number of colonies on plates. 1, 2, 3, 4, 5. Or if I measure the tail length of a mouse in centimeters, and I've just got sort of a lousy tape, I can measure only 1 centimeter, 2 centimeters, 3 centimeter. So at the moment, we have absolutely no idea. It depends on the context, right? You are absolutely right. We don't have enough information. But luckily, when we do descriptive statistics, it's not a big problem, actually. We can, in this case, it's very easy to present the data. Usually, the rule of thumb is if you have a sample size of 5 or less, you would always show all the data. There's actually no real need to summarize them, the data. So there's no need to summarize it, but for the purpose of this session, let's just simply try to summarize the data. And a very common tool for summarizing data is what is called the measure of central tendency. Measure of central tendency. This is a one-stop summary of the data. And very often, the easiest way of summarizing this data is to give the mean of the data. So mean. It's also called the average, of course. My statistics lecturer said that I was average. I thought that was a bit mean. That's a dad joke. Sorry. Don't laugh. It's exactly the same. And the mean is basically, we add up all the data and divide by the sample size. So here, our mean usually is abbreviated with the Greek letter mu, which indicates that we are talking about our data only. We don't make any weird inferences and things like that. And oops, the general equation for the mean is just simply we sum up all the data, all our observation, and this x sub I indicates the observation that we have, and we divide it by n, by the sample size. Or written out, it would be 1 plus 2 plus 3 plus 4 plus 5 divided by 5. And if my maths doesn't let me down, we would get, what is it? 3. 15 divided by 5, so the mean would be 3. So that's a nice summary. Now, of course, here our data are really nicely and well behaved. They're all nicely close together, so the mean is actually a good indicator for what's going on. And we can report the mean as mean equals 3 in this case. The mean has a slight disadvantage, however. 1, 2, 3, 400. Our data. What's the mean? Bless you. What's the mean? Sorry? So we've got now our data 1, 2, 3, 4, and 100. What's the mean? 22. Mean equals 22. You just add them up, 1 plus 2 plus 3 plus 4 plus 100. That gives you 110 divided by 5. So you have a mean of 22. Because what you see is that this single data point has a massive impact on the mean. The first 4 data, 1, 2, 3, 4, are nowhere near our mean. The last data point, the 100, is also nowhere near our data. So it is problematic to report and say, well, the mean of our data is 22. Yes, it is correct that the mean is 22, but none of the data points are even close to the mean or the average. How can we bypass this problem? What can we use instead of the mean? We can use the mean, but a mean is very sensitive to what is called an outlier, and I will show you how we deal with outliers later. What can we do? We can use actually another measure of central tendency, which is the median. In the median, what we do is we order the data from smallest to largest, or you can do it from largest to smallest, it doesn't matter. And you take the middle. So, oops, we have 1, 2, 3, 4, let's say 100. Now, in this case, it's already ordered quite nicely. And what I try to do is now I find the middle data. So what I usually do when I have to do it by hand is I just say, okay, I take them away from each end. 100, 2, 4. Oh, look, we've got 3 as our median. Cool, job done. So our median, and as far as I know, there is no standardized abbreviation for mu, like the mean. Oh, by the way, some people struggle with typing mu on a computer. On a Windows machine, you press Alt and 243 on the number pad at the same time, and it should give you a mu. How cool is that, eh? Okay, so our median now is 3. What would be the median of 1, 2, 3, 4, 5, where we don't have the outlier? It's also 3. So the median is no longer sensitive to any weird data that are sort of flying around. Okay, 1, 2, 3, 4, 500. What? Yeah, absolutely right. If it is an even number, what the hell are we doing? Let's see. 100, 2, 5. So we are left with 3 and 4, right? And in this case, we just simply take the average. So the median would be 3.5. Yeah? Happy with that? That's the median. There's one more, which is the mode. The mode is just simply the number that is most frequent in our data set. So if we've got the data set 1, 2, 3, 4, 5, we have no mode, because they all have the same frequency. But if I've got 1, 2, 3, 4, 4, 5, then the mode would be 4. Happy with that? Yeah, that's really trivial, and it's probably something that you've done at TCSE or something like that. Okay, now that was one way of describing our data. Yeah.
Then we use the geometric mean.
Let me put it this way. I'm doing statistics for the last 30 years, and I've never, ever encountered a case where I would use the geometric mean. The geometric mean is basically where instead of adding them up, you multiply them, the data, and take the nth square root of it. You could, but as I said, I have never encountered a problem where you really would need to use it. But if you have one, absolutely. You have to specify then, however, what kind of mean you are using. Make sense? Shall we do a 5-6 minute break, and then we do a measure of variability? Yeah. Okay, back at, say, 11-ish. Okay, brilliant. Thank you. Is it too simple? Yeah. Is it too simple?
So, I'm here to express the basics, so I'm happy.
Yeah.
You did that. So you're very much. For me, so hopefully this will show on the recording.
If you've got any questions.
James.
Yeah, James.
I'm really sorry if it's very sad. No, it's good. I tried doing the GRC stuff last year, and it's just so technical. It's so bad to be doing. So, yeah. I found geometric mean using personality data, where your piece like sometimes used, sometimes not, just through the nature of and you're about the same and everything. That's why it's good for. I guess if you yeah. Yeah, you can use I mean, you're not that much. And also, that always feels wrong to me.
Yes.
Go there and then go there. Oh, come on.
No.
Yeah.
You see the comments?
Yeah. But then, could you go argue that's like design problem?
Absolutely. Absolutely. So, this is just
That was the I went to
Yeah, I don't know because
that's kind of where I see people turning. You could also say, well, not necessarily next week, but get a lot done, probably stuff,
something.
I think so. The one that is asking about
Well,
no, that's fine. I think that would be the easiest way to
Okay, great, thank you.
Yes, please. As a reminder. Right. Cool. So we have the measure and we are all back, yeah? Hands up who is not back? Okay, good. Yeah, there's always one. Thank you. I can trust that. Okay, let's have a look at the, we have done the measure of central tendency, but, and we have seen that the mean is great, but sometimes if our data are too spread out, it can be slightly problematic. So in a way, what we want to do is also we want to describe our data in terms of how spread out they are. So that would be the measure of variability or variation, or you also see it as measure of dispersion. And the easiest way is just, you can formulate the range. So if we've got 1, 2, 3, 4, 5, our range would be just simply from 1 to 5 with a mean of 3. And that's, that's fine. That, with that, we get a good idea what the data look like. We could also ask, how far away are our individual observations from, let's say, the mean? How can we do that? Okay, we've got our data. This is our mean. That was 3. And our first data point is here, 1, 2, 3, 4, 5. These are our data points here, right? And we can now say what on average is the distance from each observation to the mean. So could take the distances here and take the average of that. So we would calculate our observations. 1 minus 3 plus 2 minus 3 plus 3 minus 3 plus 4 minus 3 plus 5 minus 3. And then we divide it by the number of observations that we have, 5. Right? And that would give us on average the distance of each observation, when we sum it up, the average, from the mean. Or does it? Does it? Does it, if we add this up, does it give us an indication how far on average the data are away from the mean? What do you get if you sum that up? 0. Bugger it. It means, actually, on average, our data points are absolutely not different from the mean. Wow, whoa, wait. Of course they are different. I mean, look, here, 1, 2, they are certainly different from the mean. Okay, the 3 is on the mean, but 4 and 5 are different from the mean. So we can't use that method. Why can't we actually use it? Because in the first place, here we get a negative number, -2. And this negative number here cancels out with this positive number here. Likewise, here we get -1, and that cancels out with that number here. So it is these goddamn negative numbers that cause all the problems. Right? How do we get rid of a negative number? There are 2 ways. What can I do to remove the negative sign? Square it. Brilliant idea. What is the other method? Take the absolute value. We'll discuss both. Square it. Wonderful idea. Let's square it. Let's try to think about it conceptually, what we are doing. What we do is we calculate the square of the difference. By the way, before I do that, what we have done here is where we take the difference between an observation and the mean. These differences, if we don't square anything, they are called residuals. So 1 minus 3, that is a residual, -2. 2 minus 3 is -1, that is a residual. So they have a name, these things. And what we are doing now is we square the residuals. We square the residuals and take the average of them. We basically take the average square size. So what we do is we square everything like that, because that gets rid of the negative sign. So 1 minus 3, that's -2. -2 squared gives 4, right? 2 minus 3 gives -1. -1 squared gives 1. 3 minus 3 squared, 0. 4 minus 3 gives +1. Squared is 1. And the last one, 5 minus 3, that is +2. Squared is 4. and we divide it by 5. So we've got 4 plus 1, that's 5, plus 1 plus 4, that's 10. 10 over 5. That would be 2. Absolutely right. So what have we done? We have taken the sum of observation minus the mean squared divided by n. Okay? Happy with that? That is basically our equation. We take the sum of the squares of the difference, basically. Yeah? This thing is quite important. It even has its own sort of symbol. It's a sigma squared. And this thing has a name. What is this called? I hear variance, I hear standard deviation. Only one is right. This is called the variance of our data. That's quite important. It's the variance of our data. And we divide this variance of the data. Remember, we are in descriptive statistics. We just want to describe things. It's the variance of our data. We divide it by n. Brilliant. It has a problem. Houston, we have a problem. Can you anticipate that problem?
Is it not kind of in itself skewed because stuff that's 2 units away comes?
Units are. You're going in the right direction. Let's have a quick look at what we have done with the mean and things like that. Let's say these are measurements in, say, centimeters. Yeah? So here our mean, mode, median would be, let's say, mean equals 3 centimeters. And that makes sense in a way because we measure centimeters. What is the unit for the variance? What did we actually do? What is the unit for the variance? You're absolutely right. It's centimeters squared because we take the squares. So the variance would be centimeters squared. For people who look at our results when we report them, it is, okay, the mean is 3 centimeters. The variability is 2 centimeters squared. Panic. What does that mean? Why is it squared? So it's centimeters squared. How do we get rid of the square? Square root. So we take the square root of the variance is just simply the square root of what we had here divided by n. And that would be just simply sigma. And now you are right. This has a name. This is called the standard deviation. So the standard deviation is nothing else but the square root of the variance. Job done. What's the unit? It's centimeter. Hey, we are in the same system again as with the mean. Isn't that cool? Just by this simple trick. It has a slight disadvantage again. Because if you think, can you spot the disadvantage of this method, of this variance? Complicated. Oh, you haven't seen anything complicated yet.
Slightly away from the question I'm asking in the first place. No, the average distance from the mean is not exactly that.
It is to a certain degree because, well, it would be, yeah, I see where you're coming from, but it gives us an indication of how far the data are spread out. If I, for example, use the data set 10, 20, 30, 40, 50, much wider spread out, then it would be the standard deviation would be 20, indicating they are wider spread out. Yeah? But there is another problem that we encounter, which we already have seen. Because what we are doing here is actually we take the mean of the squares, right? But what if one square is really big? It will sort of bugger up our mean. So variance and the standard deviation are, like the mean, very sensitive to outliers, to large values. So if we've got the value of 100 instead of 5, we have a problem with our variance. It's just one data point that messes everything up. So if our data are nice, like this one here, 1, 2, 3, 4, 5, then by all means, use the mean and do the variance and the standard deviation. But if you've got some rogue data in it, and we still want to report sort of an overview of our data, we can use another method. And this time, we make use of what we have learned today already with a median. We can use the median also to figure out what our data would look like when we look at the dispersion, at the variability. How do we do that? Okay, so we've got 1, 2, 3, 4, 5. That's our data. And they are still nicely behaved. Don't get me wrong. But this method that I show you basically uses the median, and very often this is indicated by an X with a sort of a squiggle on top of it. That's the median. We said the median here is 3. We take the difference between the observation and the median. So we take the difference, xi minus the median, which would leave us exactly again with the issue of the -2, -1, and so on. But this time we get rid of the negative sign, not by squaring, but by taking the absolute value. So we have 1 minus 3, 2 minus 3, 3 minus 3, 4 minus 3, 5 minus 3. And for each one of these values, we calculate the absolute. So 1 minus 3 is -2, but the absolute value of -2 would be 2. We just ignore the negative sign. 1, 0, 1, 2. Cool, eh? So we have transformed our data set. And what we do now is we order our data. We have 0, 1, 1, 2, 2. And now we take the median of this data set. So we take the median basically twice. Median would be 1. So our variation in this, with this method, gives us a value of 1. What's the unit? Well, we haven't done any weird squaring, so the unit would be still in centimeters. Does anyone know what this method is called? What the value that we get here is called, this 1? No? It is actually the median of the absolute difference between the observations and the median. That is what this thing is called. But nobody calls it like that, because you are actually going mad if you write that all the time. So therefore, it is called MAD. This is called the MAD. It is a perfectly valid measurement of how far the data are spread out. You just need to understand what it means. How does that overcome our problem if, for example, one of the data points is rogue? If that is a data point, let's say, instead of 100, let me just change the color. Instead of this 5, we have 100 here. We couldn't do the variance, we couldn't do the standard deviation, because that is very clearly an outlier. That's really bad. But what happens with our MAD? So we would get here, oops, go back. We would get 100 minus 3. That would give us 97, right? So this value here would be 97 if we ordered that. Does it affect our second median? No, it doesn't. It's still 1. So we have basically one rogue data point. We can eliminate that guy just simply by using the MAD instead of the variance and the standard deviation. It's pretty cool, eh? Now, if somebody, just a sort of word of warning, if somebody publishes a paper and they put in the median and the MAD for the variability, the MAD, what should you do? Answer, look very carefully. Because it means they do that for a purpose, because you know, nobody in their right state of mind would use the MAD if you can use a variance or standard deviation. It is an indication that the data are probably not terribly well behaved, that there are things that are a bit weird. Okay, happy with that? So you can do the MAD, you can do the variance, you can do the standard deviation. How do we present our data? Well, if we've got 5 data points, it's trivial. But if you've got lots of data points, it's a little bit more interesting. One very common method to represent the data, and let's go back to 1, 2, 3, 4, 5, is, and you can do that basically with any data that you have. You just take the median that we have done. Okay, that's this one here. 1, 2, 3. So that's our median. And what does the median actually do? It splits the data into a lower half and an upper half. So the lower half would be 1, 2, 3. The upper half would be 3, 4, 5. And what you could do is you then can say, okay, the lower half, why don't I find the median of the lower half? What's the median of the lower half? 2. What's the median of the upper half? 4. Absolutely. So what I can do is I can sort of draw a box Here is the median, was 3, that is 2, and that is 4. So I've got a nice box. What do I do? And how many of my data points are actually located in this box? If you think about it, we've got 2, 3, 4. In a way, it would be, if you see it like the way we've done it, 1, 2, 3, and 3, 4, 5, it would be 50% of the data that are located in this box. And what we do is we chop down our data into what is known as quartiles, into 25%, into quarters, basically. This thing is called the interquartile range. The interquartile range contains 50% of the data. And you can do that with any data set. It doesn't matter how big it is. Interquartile range, usually abbreviated as IQR. What do we do with the other data? So we've got 1 and we've got 5 still. How can we indicate that? Well, that's very easy. We can do that by just simply saying, okay, we have one more data point, that is 5. One more data point, that is 1. Here. This is our IQR. This here is the first quartile. This is the second quartile. Third. And that would be the fourth quartile. So we split our data in 4 equally sized ranges. This depiction, and it can be either horizontal or it can be vertical, has a name. What is it called? Is that a question mark at the end? You say box and whisker plot. Are you sure? Would you bet your first unborn child on that? Yes, good. You're absolutely right. It is called a box and whisker plot. Box and whisker. The whiskers are these things here, and the box you have as the interquartile range. Fantastic. Right. Now, what do we do if we've got 1, 2, 3, 400? We still can do our box and whisker plot, right? Let's quickly do that. So that's 3, 2, 4, 1. Now, what do we do with 100? A very long line, right? Actually, no, we don't do that. Because very clearly, this 100 is a data point that shouldn't be there. That's an outlier, right? What we would do in this case is we would try to figure out where are outliers placed? And we can do that by saying everything that is larger than a certain criterion. Let's put the criterion here, roughly here. Anything that is larger than this point here, and anything that is larger than this one here, we consider as outliers. So our 100 would probably be way over here. We would just indicate with a star or a sign and say, oh, that's an outlier here. And outliers we don't connect with a whisker. How do we find this outlier? Or how do we find this sort of this fence here? Actually, it has a name. It's called a two-key fence. Has nothing to do with a turkey. It is named after the American statistician William Tukey, who came up with this. This two-key fence is actually given by the value of 1.5 times IQR. And here also 1.5 times IQR. So IQR, our interquartile range was 2. (1.5 times IQR, that would be 3. So this point here would be 4 plus 3, that would be 7. Anything that is larger than 7, we would consider an outlier. Likewise, here, 2, and I should do that here, 2 minus 3 gives us -1. Anything smaller than -1 would be considered an outlier. So 100 definitely is an outlier, no doubt about it. That's the IQR method, and that is fairly straightforward. So all you need to do is find the two-key fence, 1.5 times IQR, and you can see, oh, I've got an outlier. What shall we do experimentally with outliers? Outliers. Ugh. Carpet. Outlier. Nobody saw it, right? Answer, what do we do with outliers? It depends. If it is a slip of the pen, and if it is obvious that something really is trivial, then we probably need to record and say, we've got this very weird outlier. We measured a student as 187 meters tall. I mean, surely that's a slip of the pen. So we need to note that, but we can omit it from our analysis. That's one of the very few cases where we can omit things. However, if it is not so obvious, then this is shit hot. There is something new. There's something new that we haven't, that doesn't meet our expectations. We always believe that, we've got little planets and, and now we see one planet exploding in a supernova. How cool is that? We made a discovery. So outliers want to tell you a story. Don't ignore them. They are good. That gives you papers. Okay, make sense? Fantastic. Now, last bit. I want to give you a very, very brief sort of encouragement to look at statistical software called R and RStudio. It's free. This is, I would say, industry standard. R is also a programming language, so you can write your own programs, and it's a lot of fun. As I said, download it. Here is the QR code to a brilliant website that talks you through the installation of RStudio and R on your laptop. Do not try to run R or RStudio on a tablet or on your phone. It just simply doesn't work. Sorry?
If you have a Chromebook, it's
I think there is a version for Chromebook.
So I tried it. It was asking to download Windows 10. So what I ended up doing is the cloud version.
There is a cloud option for RStudio as well.
So
As far as I know.
okay?
Yeah, that would be absolutely fine. That would be absolutely fine. I'm not saying that you absolutely 100% it is a requirement for this course, but you make life much easier for yourself if you get used to it. And how does it actually look like when you work in it? Here is just simply a data set that I've created. What you see is that looks a little bit horrible, but don't worry about it. The general theme is you have a variable and you can call it whatever you want. So for example, you call it data. And you assign something to this variable. And the way this is done in R is with this reverse arrow. So it's just a larger sign and a minus in R. And then you can, for example, assign a single number to it. So let's say data 5. Then your data is 5. And then you can do a calculation with it. So you can say data times 3, and it will give you 15. Or what you can also do is not just one data point. You can assign a whole, what is known as in analytical algebra, it's called a vector. In programming, it's called an array. You just assign a whole data set. So in our case, it would be 1, 2, 3, 4, 5. And to indicate to R that this is my data set, you put it together and put a little C in front of it. The C stands for concatenate. Put them all together. And that is your first R program that you can write. So data, the variable data, has now the information. It is all the numbers 1, 2, 3, 4, 5. Great. What can you do with it? Well, you can actually calculate with built-in functions. So you can say, for example, calculate the mean of the data. Calculate the median of the data. Calculate the mode of the data. Calculate the IQR of the data. Very easy. And it will immediately give you these data. Let me see if I can show you that. I told you, don't run it. Very difficult to see, and I don't think I can make it larger. But hopefully what you can see here is, here are the data, 1, 2, 3, 4, 5. Mean data, median data. And let's also do the IQR of the data. And as I said, it is not suitable. And it gives me the results, 3 for the median, 3 for the mean, and 2 for the IQR. It has fantastic help on it. So what I suggest is actually have a look at what's there and play with it. As I said, in this data analysis book, there are loads and loads of R snippets in it that you can use for God knows what questions you want to address in R. Any questions? My question is, what's for lunch? Thank you very much, and I hope you found that remotely useful, not too simplified. Thank you, and I shall see you next week. Be good, don't do anything I wouldn't do. Stop recording.